Uh, can you guys hear me? Yeah, okay. So my name is Sharath Lakshman, and I work on global secondary indexes at Couchbase. And most recently, I was working on a memory-optimized index. So today, we are going to walk through the internals of memory-optimized index. So in this presentation, we are going to cover the architecture of global secondary indexes, then some details on what exactly is memory-optimized index, then architecture of Nitro storage engine, which is the engine that powers memory-optimized indexes, then scalability and performance of memory-optimized indexes, and also some operational aspects of memory-optimized indexes. So let's start with a quick overview of global secondary index architecture. So the global secondary indexes are used to for speeding up your nickel queries by providing fast indexes which are ordered by secondary index fields. So it is similar to traditional secondary indexes provided by RDBMS, but in Couchbase, you can create indexes on a subset of JSON fields, and you can query based on that. So those indexes can be used to fasten your queries because Nickel will figure out the right indexes if you have created, and you can speed up your queries. So the global secondary index also provides workload isolation and independent scaling, which is a property provided by multidimensional scaling provided in Couchbase. So the key idea is that you can have different set of workloads for different type of database services, like your document writes are different from your index updates. So you can have different resources provisioned for different set of services. So that also helps you in scaling these services independently by providing different resources for each of these services. So then you can also create multiple indexes as replicas so that you can have high availability for your indexes. Then global secondary index provides scalable performance, while opposed to local indexes, which are also partitioned based on your actual document data. In that case, your performance degrades when you add large number of nodes, because every time you query, you have to contact all the nodes and do scatter-gather operation. So in this case of global index, which are separate from your data partitioning, your indexes can be scaled independently, and you can have scalable querying performance. Then other aspect of global secondary indexes is that they are asynchronously updated. So if you consider traditional RDBMS indexes, primary index, whenever you update your primary document store, if they are synchronously updated, immediately you have to propagate that change to all the indexes which are affected. So in that case, whenever you update your document, you have to update all your indexes. So if you have large number of indexes, that often becomes a bottleneck, and you incur higher latency for your document updates itself. But in this case, we allow this trade-off, indexes are asynchronously updated. What that means is whenever you update your document, it is independent from your index update, and the document changes are asynchronously propagated to the indexes, global secondary indexes. So that means it poses some challenges for implementation, but in terms of performance, your data service and index service can be scaled out in a different manner. So let's take a look at some aspect of multidimensional scaling. So the idea is you have different nodes in which you have different set of services. So the data service and index service are separated out. In this case, you can see the size of resources used for different services are separate. So that means you can scale each of the services separately. And let's say your data updates are very write intensive, and you often create small indexes based on your secondary fields. In that case, if you have if you're doing some rebalance operation in which a lot of data movements happens, so if you collocate your services along with the data service, often it may affect the performance of index service because it is also on the same node and they demand more resources. So, but if you isolate your workload in this way, you can separate out the workloads independently so that indexes are not affected by any changes in data service. Also, you can allocate like different kinds of resources for different services based on your application demands. So now let's look at the components of global secondary indexes. So we have primarily three components, projector, indexer, and GSI client. So projector is a component sitting on all the data service nodes, which is responsible for extracting the changes happening to the documents and sending those changes over to the indexer service. So the projector, whenever a document is modified, projector receives the document changes through a protocol called database change protocol. And projector extracts the necessary fields for that particular secondary indexes and send them over to the corresponding node. So the idea is that your document sizes may be large, like probably you use like larger documents with 500 KB or so, but your secondary index are based on like small subset, which could be a location like field. In that case, actual index data is much smaller than your document. In that case, projector avoids unnecessary network traffic of sending the documents over to the indexer. Instead, it extracts the necessary fields and send it over to the indexer. And projector also understands the global index topology. So because of that, it can send it to the corresponding indexer nodes according to the topology. Then you have this indexer. So indexer basically propagates or updates your index based on the changes happening to your documents. And also it creates a database snapshots. So your index queries can use this snapshot to provide stable index scans. Also, indexer handles index DDL operations like create, drop operations. Then we have this GSI client, so which is a smart client which is aware of the global GSI topology and all the metadata. So when a nickel query engine tries to interact with the global secondary indexes, it uses a GSI client instance. So it also manages the connection pooling and all the index scan operations. So in this diagram, probably you can see like data service node contains projector. Then all the documents are streamed over to, after projector extracts the data, it streams the changes to the index nodes. And within the index node, there could be like multiple indexes. And query node, query engine basically uses global GSI client to interact with the indexes. So now let's take a look at the indexer update pipeline. So the pipeline consists of like a index port, so which receives the changes which are streamed from multiple data service nodes through the projector. So once it is received, it is in a form that multiple index changes are batched together from a particular data service node. So it extracts based on the index metadata, it extracts the corresponding changes that need to be applied for each of the indexes. And it puts into a mutation queue. And from the mutation queue, it is moved on to corresponding index engine, storage engine. So we support two types of indexes currently in GSI, which is standard index and memory optimized index. So based on the index engine, it writes to the corresponding engine. So the indexer also creates snapshot according to the particular snapshot interval. So that is a brief overview of global secondary indexes. So now let's take a look at memory optimized index. So first of all, the question is why yet another storage engine or why memory optimized index? So the simple answer is like we want higher performance. So the modern hardware is like constantly evolving with large number of CPU cores and large amount of DRAM. And if you also look at our indexing architecture, if there are like lots of there are lots of data nodes, and we prefer having like lesser number of index nodes, because indexing is more like it is better if you centralize your indexes and distribute your data over hash partitioned multiple nodes. So also your data size is like huge, and potentially you create indexes on subset of fields. So it is often possible to hold your indexes entirely in memory, because they are often smaller in size. And other challenges, like even for a single index to operate, if you have a large number of data service nodes, so one indexer node may receive changes from many data service nodes. So even to maintain a single index, we need to have a very high performance single index. So that they are the key reasons why we need a very high performance index. Then also, like all the disk-oriented storage engines basically are based on the assumption that disk access is your often bottleneck. And because of that, also they are designed by assuming like your index never fits fully in memory. And so it uses some kind of paging mechanism between disk and your available memory. So all those assumptions are based on the fact that disk is your bottleneck. So because of that, fundamentally it does not have design accommodated for like a large number of CPU scaling and large amount of memory. So that means like providing more DRAM and large number of CPU cores will not scale your performance. So we need like very high performance. You just need to add more number of cores and DRAM. We need better performance. So what if we make the assumption like the entire index can fit in memory? Can we do better? That is the question. So what exactly is memory optimized index? Yeah, it's a memory resident index, which assumes like your entire index can fit in memory. And if you throw more DRAM and CPU cores, can I scale my single index performance almost linearly? If the answer is yes. So this is designed for very high performance and scalability. So fast writes and very low latency scans. So this is a very non-trivial problem, because usually when you design a storage engine, probably it may scale for a small number of cores, but not linearly for like very large number of cores. So we have an architecture which scales for very, very large number of cores, like 40 cores or 50 cores. So also, like since everything is in memory, we need fast backup and recovery mechanism, which works well on SSDs. Then we also wanted to support smaller indexing latency. What I mean is, like, as I talked about it earlier about asynchronously updated indexes, whenever a document is updated in the data service, it takes some delay to update it in the indexer, because it has to propagate the changes and they are not immediately updated. That means like there is a indexing latency involved. So if your storage engine supports like very low latency indexing, that means we can provide like scans with higher consistency. So this storage engine is written in Golang and a bit of C. So every component of the storage engine can scale seamlessly with large amount of CPU cores. So let me introduce the storage engine behind the memory optimized indexer. So we have a paper in VLDB 2006 covering the details of Nitro storage engine. If you're interested, you can take a look. So now let's look at the design considerations for Nitro storage engine. So the first one is multiple writers for higher performance. So we want to use all the CPU cores available in the system and scale our write throughput. And it is designed for write optimized system. Then lock-free data structure for high concurrency. So readers and writers never block, and we don't use any locks in this design. And that means we can do higher utilization of CPUs. Then fast snapshotting. So as I said, like if the storage engine can provide like low latency, and if it can create like hundreds of snapshots per second, then we can provide like high consistency index scans. And we also wanted to leverage optimizations for memory resident data structures. Since we assume like everything can fit in memory, can we do like some kind of optimizations to reduce the storage overhead, which are usually incurred by disk-based storage engines. So this is some overview of the layers of the storage engine. So at the bottommost layer, we have a lock-free skip list. Then that provides like an atomic store. And over that, so that provides you like high concurrency storage backend. Then on top of that, we add a MVCC layer. This layer is required to provide snapshots and consistent index scans. Then on top of the MVCC layer, we need a garbage collector, because MVCC layer, basically whenever an item is added into the index, it does immutable writes. So basically, once an item is written, it is never modified. So next time a modification happens, it has to mark the existing as deleted and insert a new item. So that means there could be like a lot of items getting generated, even though you keep modifying the same items. So in order to clear up all the unused items when the index snapshot become unused, we have a garbage collector. And it is important to have a concurrent garbage collector, because you have like large number of writers, and garbage collection has to keep up with the writes. Then we also do like our own memory management, because if you use like Go garbage collector, it is not going to scale with the huge amount of writes we are doing with a large number of CPU cores. So we have our own memory management. Then we have a fast backup and restore, which is also highly concurrent. So to give an overview of the skip list, so skip list is a probabilistic ordered balanced data structure. So it is similar to, if you look at the search algorithm, it is similar on how to do binary search over linked list. All the operations in a skip list are amortized log-n operation. So an important property is like all insert delete, all operations are like item granular operations. In case of a B plus tree, everything is page-based operations, and it happens in the 4K or whatever is your page size chunks. So the overhead is much less. Then this lock-free version of the skip list is implemented by using atomic operations such as compare and swap and atomic add fetch. So we can now look at some of the fundamental data structure ideas we are using to make the skip list lock-free. So the key idea is like all the linked list operation, insert and delete, are made lock-free by using compare and swap operations. So the first we will look at insert operation. So let's say you have two nodes which are connected, 1 and 8, and you want to add something in between, which is 4. First, what we do is like we set the next pointer of 4 to 8, and we do a compare and swap operation, and say like change the pointer of next pointer of 1, which points to 8 to 4. So once that operation is executed, it atomically switches the pointer, and 4 becomes part of the list. So if some operation happen in between, this compare and swap will fail, and it has to retry. Then we have this delete operation. So similar to the insert compare and swap, we could do compare and swap here as well. So if you're deleting 4, we can say like currently next pointer of 1 points to 4, change it to 8. But there is a problem here because there are no locks involved here. There could be a concurrent insert that is happening between 4 and 6. What that means is like if you do a compare and swap operation and do delete and insert here, there could be a case where both insert and delete operation succeeds because there are no locks involved. So this can lead to data loss, but we prevent this case by using a two-phase delete operation. So what we do is like instead of deleting by compare and swap immediately, we add we mark the node for as deleted by adding a special delete node in between. So what that means is that whenever the compare and swap happen for inserting the element in between, which is a 6, since a new node is added, that previous pointer is changed. That means that compare and swap operation will fail, and only one of the operations, either insert or the delete, can happen. So that makes sure that delete operation is always results in a correct expected linked list. So now let's take a look at how the MVCC layer is implemented. For implementing the snapshots, we define a lifetime metadata in each of the skip list node. So the lifetime metadata consists of two integers, which we call born snapshot number and dead snapshot number. And there is a global snapshot number, which is like a current timestamp. So whenever an item is added into the list, let's say like initially global snapshot number is 1. So whenever an item is added, the born snapshot number is always set to current global snapshot number. In this first example, you can see like there are 3 items with value 10, 20, and 30. So in this case, all of them have born snapshot number as 1. Then we call this create snapshot API. So what it does is it increments the global snapshot number by 1. So now it is 2. So the next set of updates, all of them will have born snapshot number as 2. So, so that also you can note down here that all the items inserted are in sorted order, which is a property by lock-free skip list. So every time you add an item, it is always in the corresponding sorted order. So these blue boxes correspond to items in second snapshot. Now, if we add more items, those items will get born snapshot number as 3. So I was talking only about inserts here. Now in this particular snapshot 3 case, you can see like value 20 and 32, which have red outline boxes. So they are actually deletes. So what delete exactly do is instead of modifying the existing born snapshot number, if you're deleting an existing item, so it will set the dead snapshot number as 3, which is the current global snapshot number. So this born and dead snapshot number is similar to a visitor's register, where whenever somebody enters a room, you say this is your enter time, and whenever leaving that room, you say this is a leaving time. Now, if you give a timestamp, you can always say whether this person was at this room at this particular time or not by looking at this enter and leave timestamps. So that is a key fundamental idea. So, so if there is a index scan iterator for a snapshot 1, so what it will do is like it will go through the entire list, but you can see that some of them are invisible. So this is an iterator for snapshot 1. So that means like everything which were created before snapshot 1 are only visible. Everything created after that will be invisible here. So in this case, everything born in snapshot 1, born snapshot 1 are visible. Now let's take an iterator, look at iterator 2, which for snapshot 2. In that case, value 32 is invisible because that was born in snapshot 3. So now let's take a look at iterator 3. So in this case, you can see like 2 items with value 20 and 32 are invisible because those items were deleted in snapshot 3. So this way, even though all the snapshot items are resident in the same lock-free skip list, this snapshotting scheme provides a way to provide a point-in-time snapshot of the database at different points whenever the snapshots are created. Now let's take a look at some comparison with the usual disk-based copy-on-write MVCC scheme. So the idea is that in a copy-on-write B+3 storage engine models, usually whenever you modify something in a leaf node, it has to do a copy-on-write of that particular node. And also, since the leaf node got modified, you have to make updates in all the parent nodes, the index levels up until the root node. So even if you change a byte in this particular node, that means like you are going to cost a lot of storage overhead because you have to copy a lot of blocks. So even if a byte is modified, you may copy like a couple of 4K blocks, which is significant storage overhead. So the write-optimized storage engine usually try to amortize this cost by batching large amount of updates and try to apply it once. But that means like you may incur batching intervals. So that means you have higher indexing latency and your snapshot intervals are going to be smaller. So in this particular Nitro MVCC scheme, as you've seen here, every time you add some item, the memory allocate is exactly equal to that particular item overhead. So also the snapshotting scheme is very lightweight. And whenever you increment, whenever you say create snapshot, it just increments the global snapshot number by 1. So this is a very lightweight snapshotting scheme. So that means like you can create large number of snapshot per second. Now let's take a look at garbage collection. Since we create like large number of versions, and we keep these versions because we need to provide these snapshot for the index iterators. So when all the index iterators for an old snapshot goes away, that snapshots become like invalid and nobody is interested in it. So we can remove all the prior versions. For that, we have a concurrent garbage collector. So the idea of concurrent garbage collector is that since you have like large number of writers, correspondingly we keep same number of garbage collector workers as well. So whenever an item is deleted, so we keep a list of items we keep the list of nodes which got marked as deleted during a particular snapshot, and that list is maintained in the snapshot metadata. And we also keep reference counting in snapshot metadata, because if there are 100 query instances query scans running against a snapshot, the reference count will be 100, and when they goes away, it will be 0. So once it becomes 0, it can go and garbage collector will go and delete those items from the skip list. But there is some more interesting case here. Here, all the snapshots are dependent. So even though the snapshot 3 has reference count 0, it cannot immediately go and delete the items immediately, because there could be an item born in snapshot 1 or snapshot 2 which got deleted in snapshot 3. What that means is an item which is live still in snapshot 2 becomes invalid in snapshot 3. So you cannot immediately delete it. We have to wait until all the readers for snapshot 2 goes away. That means garbage collection has to be performed in a sequential order of its snapshot numbers. So once garbage collection is performed, we send those items into concurrent memory reclaimer. So the memory reclaimer is the memory management part of the storage engine. So now let's take a look at safe memory reclamation. This is a specific problem for all the lock-free data structures. So the problem is this. So you have this lock-free skip list which holds different snapshots from at different point in time. So even though if you're garbage collecting some items in the skip list, there could be some other readers which will still see these items because all are part of the same skip list. So there could be so all the iterators basically see all the items, but iterators, whenever returning the items, it will make these items invisible according to its timestamp. So because of that, whenever you're garbage collecting an item, you go and delete a particular skip list node, but you cannot immediately free it because there could be another accessor which goes to that particular node and trying to get the next pointer out of that. So you cannot immediately free it because that may lead to invalid memory use. So that means we have to wait until a safe period until which no other accessors is accessing that particular node. So we have an algorithm specific for that. That is actually described in the Nitro VLDB paper. If you're interested, you can look at it. So now let's look at the Nitro backup. So whenever a crash happens or if you shut down the Couchbase server and try to restart and recover, instead of rebuilding the index from scratch, we have a mechanisms to do backup. So the backup is also concurrent. So the idea of backup is to split the entire skip list into multiple chunks of equally sized chunks based on some statistics, and and write down the item data into different shard files, and they are always in sorted order. Each file has sorted range partitioned set of items. So we don't persist all the index level data. We just persist sorted item list in each of the files. So there is one specific problem with backup. The problem is that backup also operates on snapshot. It has to be on particular snapshot. Otherwise you may have like some consistency issues when you recover back. So if you hold on to a snapshot, that means reference count for that particular snapshot is going to be more than 1. So that means like all the further snapshot garbage collections will halt, as you've seen here. So that means your memory usage can grow. So the backup has to happen faster. Otherwise, it is going to take up a lot of memory. But we prevent that problem by using a non-intrusive backup method. So instead of holding on to a snapshot, we don't increment the reference count by 1 while taking the backup. Instead, what we do is to make the garbage collector smart. So the idea is like these backup workers will work on these skip list segments and try to back up those items. But since we do not hold on to a particular snapshot by incrementing the reference count, the garbage collector may delete items which are deleted in future snapshot. But since the garbage collector is aware of the backup worker is backup snapshot, so let's say like backup is currently ongoing for snapshot 5, and in snapshot 6, a lot of items which were live in snapshot 5 got deleted. In that case, garbage collector is aware that a backup is going on for snapshot 5. So instead of immediately removing the item, the garbage collector will first remove the item from the skip list and also write those items which are corresponding to the backup snapshot to different shard files. So you have 2 sets of files, the sorted files, which are created by the backup workers, and garbage collector creates the delta files. So based on these 2 sets of files, you can recreate these skip list during recovery. So that means like it will never block. So your garbage collector keep on working concurrently without blocking. So yeah, so that makes the garbage collector faster as well. So The next part is Nitro recovery. So during recovery, either we could do like recovery of the entire skip list by reading from the file and replaying the changes. But we do more efficient rebuild, which is a bottom-up concurrent build. Since we have backup to multiple shard files, which are range partitioned and sorted, so we create this separate skip list segment in a bottom-up fashion, in which we build the lowest layer first, then all the other links are built up in a fast manner since we have the sorted order preserved. And we join all these segments together to form the full skip list. So, in a summary, the benefits of Nitro. So Nitro provides lock-free operations which allow a storage engine to scale seamlessly with multi-core CPUs. Then single index performance can be scaled by adding more workers. Then Nitro MVCC model provides fixed overhead per item. Then fast snapshotting capability allows very low latency between data service and index service. Then Nitro provides lock-free garbage collector, which is also concurrent. Then we have a concurrent backup and recovery mechanism. Now let's take a look at the, how we integrate Nitro storage engine in global secondary index. So before that, we have to look at some data structures of global secondary index. So whenever a document is indexed and whenever a document update happens, so there are two operations that happens. So first, we have to remove any prior entries for particular index. So, and after removing the previous index entry for that document, you have to add the new index entry. So in this example, you can see like there is an employee 5 document in which the current location is Mountain View, and an update causes it to become location becomes Bangalore. In this case, first it has to remove the prior entry, which is Mountain View, and then add a new entry, which is Bangalore. So in order to get the prior version of the entry, we have one more data structure. We call it reverse map, which keeps a mapping between document ID to current index item. So this reverse map is only used during the update as a support data structure, and other index data structure is primarily used for all the index scans. So this is how memory optimized index pipeline looks like. So you have these documents coming from data service nodes, then you apply a hash and mod it over multiple index workers according to the number of CPU cores. Then each writer performs the write operation on the indexes. So since we have this particular reverse map data structure, which is only used for writes, we actually ended up using a simple hash table, which is also locally partitioned. So all the reverse map is partitioned per each of the writer. So that means like you don't have to pay any concurrency cost for this particular reverse map data structure. And during the backup, we also persist only the actual data. We don't persist both main index and the reverse map. That means like we can reconstruct these data structures on the fly during recovery. So also you might have noticed here that both main index and the reverse map actually has the same data but different layout, document ID and the index item, but they are in a different layout. So that is the reason why we only persist one of the data structure, and all of them can be recreated during recovery. So also a memory optimized index provides very less end-to-end indexing latency, which is 20 milliseconds, for our standard indexes, which is 200 milliseconds. So there is one more like storage optimization we have. So the key storage optimization for reverse map is that, so you can see in this figure like the first table, which maps document ID to index item, which is our reverse map hash table. Since both of them store like same data in different layout, instead of that, we came up with a fixed overhead for the reverse map. So that means, so from the document, you calculate a 4-byte hash, and that maps to a pointer, which is direct pointer into the skip list node. So whenever there is a conflict, there could be multiple pointers, and based on that pointer, you arrive at a particular node, and from that node, you can figure out it belongs to a particular document that we are searching or not. So in this way, we reduce the overhead for the reverse map, and the cost for reverse map becomes fixed overhead of like 4-byte for the hash and another 8-byte for the pointers. So that becomes fixed overhead. So also it helps in other operations like delete operation. Whenever you have to do a delete, you don't have to pay the cost of log and lookup into the skip list. Instead, from the reverse map, you can directly reach the node and mark it as deleted. So there are some optimization for memory optimized index for array indexing as well. So now let's look at the performance and scalability of memory optimized indexes and Nitro. So this is some performance benchmark based on a number of CPU cores for both insert and lookup. As you can see, like the scaling is almost linear. So you can see in the x-axis that it is a number of cores, and we have done this test up to 40 cores, and we saw a maximum throughput, standalone benchmark throughput of 4 million writes per second, and lookup throughput of 10 million lookups per second. Then if you look at some aspect of partitioning to scale throughput, the idea is that if your data store is not scaling well with multiple cores, the idea is to create multiple instances of the data store so that you can get like total aggregate throughput. So you can create multiple partition, and each partition providing X throughput. Then if you have N partition, you can get NX throughput. But we tried out this experiment with Nitro, where we create partitions up to 4 and 40 cores, and you see the same performance throughput. That is because you don't need any partitioning, and single index can scale with a large number of cores. So this is the end-to-end performance indexing numbers. So this is the most interesting number for memory optimized indexes. So the first graph is a single index benchmark. So this benchmark was done with 4 data nodes and 1 index node. And so basically 4 data service nodes send these changes over to single index node, and whether indexer is able to keep up or not is the measurement we are doing here. So you can see that for memory optimized index, so when 4 KV nodes send 600,000 mutations per second, the indexing service is not able to keep up easily, and the CPUs were not saturated. So that was the maximum mutation rate that came from the data service nodes. And for update workload, we generated a lot of around, I think, 250K per second. And indexing service with memory optimized index was easily able to keep up. Actually, we could drive a lot more updates into the indexer by adding a lot more KV nodes. Probably in today's Revi's keynote, you might have observed 500,000 mutations per second was the update rate that they were driving with 8 data service nodes. So if you add more nodes, you can get much higher throughput. And similarly, you can see like how our standard index performance look like with similar workload. It is much less when compared to memory optimized index. Also, since there are only 4 nodes, 4 data nodes, I tried an experiment to figure out what will be the index node throughput by creating multiple indexes. So I created 15 indexes so that I can drive 15 times more load into the indexer from the data service nodes. And the maximum throughput observed was 1.6 million insert per second. And for updates, it was 800,000 updates per second. And for deletes, also similar to the insert workload. So the reason why the update workload update is much less than index insert is because every update consists of a delete of previous item and insert of a new item. So it is almost doing same number of operations, but end-to-end operation is half the insert number. So the bottom line is like we can get much higher write performance with memory optimized indexes. So this is some Nitro recovery performance number. So it recovers pretty quickly with large number of items. So you can see like 300 million items recovers in 40 seconds. And this is like standalone Nitro benchmark. Probably with whole indexer stack, probably it's less than a minute or so. So now let's take some overview of operational aspects. So the question is how to configure memory optimized index. So whenever you set up your cluster, you have two options. Either you can choose standard index or memory optimized index. And other question is what happens when you run out of memory? And if you, ideally you should provision it correctly according to the capacity planning spreadsheet. So in most of the cases, according to our calculations, it is almost the same as overhead is always like easily calculated. So unlike like probably with standard index, probably the overhead, because of disk involved, most probably the calculation may be a little bit off. So for memory optimized index, if you provision it correctly, you can get the correct sizing. But in cases where like if you run out of memory because you have some operational load spike or something like that happens, so indexer instead of crashing, it will run into a mode called pausing. So it runs into pause mode, and what that means is like indexer will just pause. So you also get some alerts in the Couchbase UI or based on REST endpoints, and you can go and remove some of the indexes and relocate them into another index nodes. So that index node becomes unpaused again and resume its operations. So once you restart Couchbase server, since we do backups on disk or SSDs, it can recover pretty quickly as well. Then what is the recommended DRAM or CPU configuration for using MOI? I would say like use large number of, you can, if you are like very high write intensive workload, you can provide like a machine with large number of cores. It can almost scale linearly for your write performance. And we have like pretty much large number of clusters in production running with large amount of RAM as well. So yeah, that's it about global secondary indexes with memory optimized mode. So the summary of the presentation. So we presented global secondary indexing architecture overview, which global secondary index provides independent scaling and workload isolation. And Couchbase 4.5 features memory optimized indexes, which can provide superior write performance. Then we introduced Nitro storage engine with features such as multiple writers with lock-free operations, fast snapshotting, then concurrent non-intrusive backup and recovery. Also, memory optimized index also leverages several storage optimizations to reduce memory consumption. We showcase the performance for Nitro as well as memory optimized index and how the end-to-end performance looks like. So if you want to know more details about the architecture of Nitro, you can always look up for the Nitro VLDB paper. So it only takes a few minutes to build large indexes with memory optimized indexes. So thank you.